the subject of my presentation is slightly different from the previous ones. We have to look up now, to the sky. The structure, I will introduce the European Space Agency as a space agency for Europe and give some information about where these, where the assets are positioned, to which threats will be applied. So after some introduction on this, I will go more specifically on threats, on what can happen, on what is feared about the space missions, and what the countermeasures to be taken can be, have been in the past, and are now being modified because of the difference and evolution of the threats. And then I will give a few of the examples related to the missions that I introduced at the beginning on what are the measures or what will be the measures taken in order to protect them according to these threats. So the first point is introduction of ESA. ESA is an international organization based in Europe with the purpose of promoting space research and applications in space for peaceful purposes. It was founded in 1975 and it's present in the whole world because when you have to drive satellites, the ground stations must be always underneath the satellites, so they cannot be located only in Europe, they have to be located everywhere on the surface of the Earth. There are 30 sites connected by the ESACOM wide area network, which is something that I developed in my previous job in the agency. About 4,000 users, extreme variety of users, managers, scientists, technicians, administrators, astronauts. There are people up in space, always at any given time. Politicians, citizens, and users, all of you could be part of this network. The purpose of ESA is to design and implement space missions and to operate only a few of them, because the purpose, the political drive is to develop missions and to deliver them to other organizations who operate them. The only missions that are operated directly by ESA are the scientific ones and the Earth observation ones. The others are transferred to other operators like EUMETSAT, Eutelsat, the future Galileo operator that are operating and possibly making money out of these missions. There is a high degree of interaction with national space agencies, European space industry, of which two are the main players, EADS, which is the Airbus consortium, and Thales Alenia Space. And then there are many other smaller ones. And international space agencies in missions that can be together with US, Russians, and so on, Canadians. The member states of ESA are today 20. There are 18 of them are members of the European Union, and 2 of them, Switzerland and Norway, are not, so they are actually cooperating with ESA on their national basis. There are other countries that are providing or planning to access. These are basically the other members of the EU that have not entered into space yet. As you can see, of the new EU member states, the ones that have entered the European Space Agencies are those that were formerly space powers in the Soviet bloc. Poland, Czech Republic, Romania, they had astronauts, they had actually space programs, and they have therefore a space industry developed and ready to cooperate. And there is Canada, which is taking part in many of the missions under a cooperation agreement. Now, this is the geographical location, which is quite dispersed, as I was saying. The headquarters is in Paris. The main site is in Holland, in the Netherlands. It's called ESTEC, European Space Technology Center. And this is really like a big factory where satellites can be tested. There are testing facilities that can simulate space environments on the Earth. This is very important because before a satellite is launched, it needs to be thoroughly tested in all its functions, electrical, but also physical, in terms of shaking, radiation, temperatures. Then there is the control center in Darmstadt, which is basically where all the consoles are, where they say, instead of saying Houston, we have a problem, we say Darmstadt, we have a problem. But normally we don't have problems, so this never happens. The astronaut center, the training of the astronauts is in Cologne, is actually a facility where astronauts can also simulate space environments. But in reality, nowadays, astronauts are all trained in Moscow, in Star City, because there's only one way to go up to the space station today, via the Soyuz, launched in Baikonur. So there is no basically other way for any astronauts of any nationality in the world to go up today. There will be a new launcher by the Americans, but this is still a long way to go. And as you all know, the shuttle has been pensioned, retired. Then what's relevant is the triangles. The triangles are the ground stations. The ground stations are antennas, big antennas or small antennas, where the telecommands, this is relevant in this presentation, where all the communication between the ground and the satellite is taking place. And 3 of them in Cebreros, in Malargo in Argentina, and in Unorcha in Australia are big space stations, are big ground stations, 35 meters, and these are for deep space. They are meant to reach probes and satellites that are far away in the solar system or even beyond. Then another important point is the launch basis, which is in Kourou in the French Guiana. The importance and the success of this based facility is its proximity to the equator that makes it possible to launch cheaply satellites that have to reach the geostationary orbit 36,000 kilometers high, because it goes up only vertically, so it needs less fuel. Other bases like the one in Baikonur or the one in Cape Canaveral in Florida need to go diagonally if they have to go up to the geostationary orbit, so they need more fuel, so they're more expensive. And that's why the program, the European Space Program, which is made of 3 launchers nowadays, the Ariane 5, which can launch 12 tons, up to 12 tons of payload, the Vega, which can launch up to 1.5 tons, and the Soyuz, which is the Russian launcher, which has been transferred, rebuilt, and successfully tested in Guyana, can launch up to 6.5 tons. Now, let's go and take some examples of the missions. The interesting aspect of ESA is that it can cover all different types of missions. Other agencies like NASA, for example, cover only a few of them, leaving to other parts of the country, for example, the DoD, other types of missions. Space science, human space flight, exploration, Earth observation, launchers, basically these programs I mentioned, navigation, telecommunications, technology, and operations are all part of the coverage of the functions of ESA. Now, what about security? There is a dual aspect of security that needs to be taken into account. One is that space missions have a value to the European citizens because they bring data, they bring elements that are relevant to everybody's life. And new needs for security that came up after the 9/11 incidents have developed into a European security and defense policy that sees space assets as fundamental for the creation of security systems based on Earth. In particular, the data that can be obtained from space and the value of the assets that lead to and from space themselves that become fundamental elements in the critical infrastructure of the European, in the critical elements of the European infrastructures. And another important aspect is that synergies among civilian and military activities, terrestrial and space-based, is being built with the need to create and to protect data at different levels of classification. So there is a whole family of measures that need to be taken, we will see them, to protect the different aspects and the different kinds of the data related to a space mission. In practical terms, what are we talking about? This is what the politics have decided in the European level council, in the European Council at the ministerial level, which takes place only after every so many years, by focusing on aspects related on security on Earth and security in space. Security on Earth, we talk about the protection of critical infrastructures seen from space, the same infrastructures of space themselves, but also infrastructures like bridges, trains, nuclear power plants, all kinds of critical infrastructures that can be detected and can be well observed from space. Maritime and land surveillance, because with the Earth observation satellites, many of these aspects can be seen and analyzed with very important data obtained from space. Humanitarian crisis support and rescue tasks, because when there is a problem, for example, a flood or an invasion or emergencies of humanitarian nature, data from space can be fundamental to intervene timely and with accurate protection and with accurate precision where it's needed. Public safety, including civil protection. This can have to do with earthquakes or with natural disasters, and other emergent security threats like climate change. There's a number of important missions that are trying to detect and devise details about the climate change, which has been significantly different in the last 30 years respect to the past. And all of this can be observed from space. Another important aspect, which is relatively new and relatively relatively recently made into the press, is the space situational awareness, which is the observation of objects in space that can be satellites, that can be debris, that can be also asteroids or meteorites, that once observed can be can lead to countermeasures that are taken in order to improve the situation and possibly avoid further damage. You all know about the recent fall of meteorites in Russia that has been lately detected, and so evasive actions couldn't be taken because there was at the same time another, that was a very unfortunate coincidence, because in the same day there was another expected asteroid coming somewhere else, and all the attention was on the other one. So the effect was damage, relatively small damage, but still something that could be avoided and could have been prevented. Now, of the current ESA missions, just to set the stage for the threats, there are a number of missions oriented to science, like Venus Express and Mars Express, that are twin orbiters around the two planets, and they have been orbiting for years around the two planets. Normally at this point the question asked is, did they detect Martians or Venusians on the surface? And the answer is, we know, but we cannot tell you. So the answer will still remain in your curiosity. The space station, which is orbiting the Earth about 350 kilometers high, and it's always populated with astronauts, has significant European contributions. The Columbus Laboratory, which is a laboratory where experiments can be performed, and the experiments are always interchangeable via the probes that can go to the station to bring these experiments that are racks like a fridge, so they can be moved out and in interchangeably at every mission, via this vehicle, which is called the ATV, the Automated Transfer Vehicle, which is unmanned, so the astronauts go with the Soyuz, but is capable of bringing load and bringing back debris, and then it burns, re-entering into the atmosphere. This is the artist's view of the ATV, which is completely automated and docks to the station. And another interesting mission is the Rosetta probe. The Rosetta probe is a sign of patience of scientists, because it was launched in 2004, and it will land on a comet beyond Jupiter in 2014. So these people for 10 years have been following the probe, turning it on every 6 months, and then waiting for it to go to sleep and to come back again. And next year is when it actually will perform its landing on the comet. And the theory here is to discover, because there is a theory that says that comets are made of cheese, and we are not sure about that, and we want to see when the probe will land, whether that's verified or disproved or made of something else. Okay, now we go to the mission which is the center, the main focus of the center in Frascati where I'm based, which is Earth observation. It was always called GMES, Global Monitoring for Environment and Security, and now it was called Copernicus because there was Galileo, so they decided to use name of scientists to call the mission. So this is a recent christening of the name Copernicus to this mission. It's an Earth observation mission based on a number of satellites, the so-called Sentinels, following the example of meteorology, but for other domains like emergency management, air quality monitoring, land monitoring, ocean and ice and sea ice monitoring, and so on. And there is a whole lot of new science which is being created and in preparation for the data that will come out of these missions. And this is the family of the Sentinels that will be launched in 2014, 15, 16. Sentinel-1 is imaging of small aperture radars. Sentinel-2 is multispectral imaging. Sentinel-3 is ocean and global land monitoring. Sentinel-4 will be geostationary, so it will go far away, and it will be monitoring the atmosphere. Then another important family of mission is Galileo, satellite navigation. It's a system under full European control, developed by ESA and funded by the European Commission. It will constitute of 30 satellites inclined on 3 circular orbits inclined at 56 degrees at the altitude of 23,000 kilometers, offering to Europe and to the world accurate and secure positioning with various levels of precision. The user access is defined and controlled, so there will be a policy to access the user, to access the services, in particular those services that will be for governments through appropriate key management. We will see the details about that. And potential applications under consideration are internal security, law enforcement, customs, critical transports, air and sea navigation, energy, telecommunication, emergency services, and defense. The 4 of these satellites are already in orbit, and so that the signal could be determined, so that today already test navigators can still receive and work on the signal with 4 satellites, so not a lot of precisions. And the next ones will be launched starting of next year. Then we talk to the threats to the space missions. Let's look at what are we afraid of and what can happen. As we have already defined, there are ground stations on the Earth connected via a ground network. There is a control area or the control segment, which is the control center and the number of decisional power, like the scientists that individually control the instruments on board from their own universities, from their own centers. So as you can see, there is a high degree of interconnection on the ground. And there is a big number of users that can directly or indirectly take advantage of all the data that come from space. The space elements are up there in space at different altitudes on different orbits. There are whole different families of missions that are performing their own scopes. But they're all characterized by the fact that from the control center, there is a set of telecommands that we will call TC, telecommands, that can be sent to the satellites to tell them what to do. There can be attitude telecommands. They can have to do with instruments on board. They can have to do with levels of the positioning in respect to the sun, the positioning in respect to the ground. They need to observe particular situations. So all of this is determined by a mission manager in the control center. Then we need to know what's happening on board. So there is a number of housekeeping telemetry data, which is coming down from the spacecraft to the Earth to tell us what is the status of the instruments, of the level of power, of all the different parameters that on board are telling us about the status of the mission. In addition to this, there's the payload data, the function of the mission. If our purpose is to observe an iceberg, the data about the iceberg will come down as payload. If our purpose is a positioning signal, the payload data will be a number of positioning information that will allow the receiver to know where it is. This is basically the fundamental reason, the raison d'être of the... I went too fast. Now I need to go back. The raison d'être of the mission itself. The payload data gets then elaborated in the control center and transformed into products. For example, the Google Maps that you see are satellite data that are transformed. They're visible, they're optical, and they tell you what a particular piece of the surface of the land looks like when after processing by the control center. The product's data are normally made available to the public based on a number of, on a specific data policy. The data policy can be, I make this available to the principal investigator who is entitled to use the data for 1 year and publish about it before the data is made public to the rest of the world. It can be the end users who have interest on the data. It can be civil protection, it can be maritime authorities or whatever, depending on what the purpose of the missions and how it has been defined. Okay, now, what can happen to a space mission that we are afraid of? Because after all, we are talking about assets that are up in space. They're very valuable, but nobody can make money out of them because you cannot steal them. You cannot sell the pieces of hardware that are there. So what are the potential targets for cyber attacks? The user segment, including the equipment, is the data collector, demonstrators, prototype, commercial services, or applications. So to start with, money can be made duly or unduly by abusing the data coming down from space. About the space segment, we are afraid of the well-being of the satellite, of the launchers, on the onboard equipment, on the human lives that are in the space station of extremely high value, onboard equipment and scientific experiments. Since there is a data policy behind it, it is possible that this is abused and data is accessed unduly and contrary to the data policy. And then the ground segment is a set of assets. I mean, one of the most common threats and one of the most common risks is that somebody breaks in a ground station and steals the equipment contained in it. Some of the ground stations are in areas that are poor, so there is actually quite some social unrest with respect to the fact that there are people well paid who are thrown into a location and have a very high standard of living with respect to the towns where they are normally located. So there is also this kind of risk. Now, all relevant types of Earth-centric and Sun-centric orbits can be attacked in different modalities. What are the attacks that we're afraid of? Mostly, and more seriously, is ground to space. We are expecting the threats normally coming from space, from the ground. Traditionally, until a few years ago, in order to do damage to a satellite, it was necessary to build a ground station, to obtain direct access to space. And the cost of the ground station is in the order of millions, if not tens of millions or hundreds of millions. The big stations, the one with 35 meters antennas, are in the orders of hundreds of millions. So the threat was limited to a few countries, a few states that could be threatening. Remember that there is a treaty from 1966, the Outer Space Treaty, that rules very carefully, and it's similar to the Treaty for Antarctica, that rules carefully the use of space and the access to space according to rules of common access. So a country, in order to have access to space directly via a ground station, would have to be really against all rules. And this is not happening, or it has not normally happened. But then, the new part is that access to space can be gained via the interconnection, or thanks to the interconnection of the ground networks controlling the satellites with public networks, which has happened in a way controlled but often uncontrolled, via the rooms, the offices, the homes of everybody. And that's what is actually happened. These are the new threats. Then the threats can be space to space. Now, of course, our thought goes immediately to aliens, to beings that are not from our planet. This we haven't seen, or at least we cannot tell you about that. But in reality, space-to-space threats have occurred. There is a landmark date, the 11th of January 2008, when the Chinese destroyed a Chinese satellite. They had actually built a so-called kinetic probe, which was basically like a torpedo. They put it in space in the trajectory of one of their satellites, and the two things collided, and the satellite, the Chinese satellite, which was non-operational, but it was full of hardware and equipment, exploded, broke down in thousands of little pieces, making orders of magnitude bigger the problem of space debris. So this sounds strange, but it actually happens, and it has happened. Space to space. And then space to ground, the satellite can be itself a threat because in its re-entry, because these satellites re-enter on a regular basis, needs to be controlled, needs to be destroyed by burning in the atmosphere, and this is true since 2006. There is a code of conduct, which is a treaty that has been stipulated between the space powers, so that the last portion of the fuel, of the onboard fuel of a satellite, needs to be used to the orbit to throw it down, in order to avoid, or to put it in orbits that are highly eccentric so that they are not dangerous, in such a way that the satellites, when not operational anymore, will not be a threat to other satellites. Now, going back to the model that we had, let's see systematically what these threats can be. To the space elements, the space elements can be damaged and are actually damaged by space debris. But the link, the communication link from the ground to the spacecraft can be jammed. By jamming means noise that is generated artificially and can damage or prevent normal communication. The same as a denial of service attack. The telecommands can be replayed, or they can be counterfeited. Normally, the telecommands are like TCP/IP. They are a protocol which is well known and published in books, because it is important that the knowledge about the telecommands is shared, so that they can be, for example, in a particular emergency, an American ground basis can be used to send telecommands to European satellites to save it or to recover it. So there is a quite common knowledge in the syntax and in the way the telecommands look. Replaying a telecommand can make a disaster, because the satellite can be turned 2-3 times, the same telecommand, and it doesn't know anymore its position. The payload and the housekeeping telemetry can be intercepted and can be abused for many other purposes related to the non-observance of the data policy. On the ground, we come into more classic scenarios, but on the ground, the station can be accessed by unauthorized intruders that can be either insiders, the classical problem with the insiders, or with the outsiders. And social engineering can lead to the possession of all kinds of equipment, and including the data, and including the knowledge, password keys about the satellites. The data itself can be intercepted on the ground, stolen, hacked, and last but not least, the quality of the software can affect the well-being of the missions. The most brutal and one of the biggest disasters in space is in 1997, took place in 1997 with the first Ariane 5, the Ariane 501 launch, which exploded, or actually was made to explode a couple of kilometers high in Kourou, because the attitude of the flight was compromised, and this was a software flaw. This is in all books of software, because it was a piece of code that was reused from a previous version of the Ariane, from the Ariane 4, and the counter that was counting a parameter was not properly sized and was not properly checked. All those who have taken a programming course know that you have to check an exit code when a counter goes up. This counter went up beyond its value and became 0, because the 1 went to the place where there was no place for the counter. So became 0, and the launcher took the horizontal attitude, so it would have been falling somewhere else, and so it was made to explode. This is a clear software threat. Software methodology needs to be developed in order to cope with this kind of disasters. Now, about the hacking in space, there is evidence. It does happen. And there are 2 cases. One on October 20, 2007, the Landsat 7 was experienced 12 minutes of interference, and the responsible party did not achieve the steps necessary to command the satellite. But less than 1 year after, in 2008, Terra-EOS, which is another Earth observation satellite, experienced 2 or more minutes of interference, and the responsible party achieved all steps required to command the satellite. So these events happened, and they were not published. The publication took place, you can see the press, in 2011. So there were 3 years between the occurrence of the events and the publication. Because the embarrassment of the victims of NASA, in this case, was so high that they didn't want to share this knowledge with the public. And it leaked out in the course of the years. What was the problem? The problem was that those who affected, the perpetrators, were sitting at home. It was not a classical penetration like those with a big ground station or with somebody entering into the base or paying an operator or somehow getting the operator to do the damage. This was actually pure hacking from public networks. What can we do about that? Well, there is a whole science that has been developed traditionally and now suited to the needs. And you can imagine this becomes more classical respect to the previous presentations. You can imagine that the source and the solution of all of this is cryptography. But before that, for the space elements is redundancy. The Galileo satellites will be 30 satellites, but you can get your position with 6. So there is a high level of redundancy in such a way that the satellites will be somehow abundant or redundant respect to what they have to do. And situational awareness, to have observation capabilities in order to know exactly where the satellites are, not only the satellites, but also the debris, the pieces of hardware that could do damage to them, in such a way that evasive measures can be taken whenever necessary. This happens all the time with the space station. Situational awareness detects debris that can be dangerous, and the space station is moved as necessary to evade them. Then, the simplest measure is telecommand authentication, so that the telecommands will have, and then you need a crypto processor on board. Once the satellites are provided with some crypto capabilities, then the telecommands can be authenticated, and there is a number of standards and a number of ways to do it, so that the receiver, the satellite, will know exactly who is sending the telecommand, sequencing, and all the necessary capabilities, the necessary functionalities in order to make sure that they are legitimate. In order to do this, you need to have keys. So the whole problematic of keys on board needs to be taken into account. The traditional one we will see is to put keys on board before the launch, and then you can renew the keys via a key authentication and a key renewal process, depending on the rate of the data. Then, at the ground, we have end-to-end security, physical security, protecting the ground stations, inserting them in the national legislations as critical infrastructures, vetting the personnel so that the people who work inside the stations are trusted, and then, if necessary, classifying the information, which goes in the direction of missions of dual use with the military or with the authorities, civil protection or police authorities. All of this is a whole family of missions that are in the new making. Then, in terms of the protection of IT systems on the ground, the information assurance philosophy, which goes in the direction of risk assessment, ISO 27001, ISMS, monitoring and continuous improvement in the plan, do, check, act cycle of the infrastructure, becomes mandatory. And that's why there is a process ongoing for the certification to the ISO standards of all the IT systems, and the mission information system, the one based in Darmstadt, has been the first one to be certified in April of this year. Then there is a whole family, this I will go fast because I want to come, basically there is a whole family of mechanisms that can be adapted to the applicable threats that we have seen. I just pick one. For the interception, common products off the shelf can be used to protect the traffic via encryption, frequency hopping, spread spectrum, and protecting the archive and distribution of systems via encryption. There is nothing against putting the mission data in the cloud, and actually this is being done progressively. There's more and more of the mission data which is put in the cloud. But in the data of more sensitive nature needs to be encrypted according to commercial or traditional systems of encryption that can be used in order to protect the data once it's made available and accessible only to those who are entitled to do it. For what concerns jamming, for example, multiple uplink paths and multiple access points are being taken. There's always redundancy in the ground stations. So there's always 2 ground stations behind the spacecraft that can be used in alternative paths in case some of the links are jammed. Now, what I want to come is to an important point having to do with mission economics. As we have seen in the examples, not all missions are of the same threat profile. Traditionally, the scientific missions are more liberal in the availability of data. But still, we are not talking about full availability because it's a fundamental point of space missions that the principal investigator, the scientist who have proposed the experiment, owns the data for 1 year, because he has the right to publish and to get basically the mileage that gets out of the findings in time to get publications, to get fame before the data is made available to the others. In any case, the scientific missions must be characterized as among the most liberal. Earth observations is more sensitive because some of the Earth observation data may have to do with movements of troops, with movements of ships, movements of a typical example we make is the crop of coca in Colombia or in the valleys of Peru. This is very interesting, but some of the people that are dealing with that may not be happy that the general public can see exactly where the crops are grown. So there are threats that need to be taken into account. For what concerns the navigation, as I mentioned, the navigation signals are in general available to the general public for positioning, but there is a number of signals that are encrypted and available only to specific authorities in terms of because of precision and because of the fact that they cannot be disturbed in any critical situation. In that case, keys need to be handled, so there is a quite level of security inside it. Meteorological data, and then main space flight and exploration have to do with human lives. So it's fundamental that the data are properly protected. It's not possible. It is possible to joystick the levels of the oxygen in the space station, but we don't want this to be made available to the general public. That there is like a game on on how long will Mr. Parmitano, the European astronauts currently on board of the space station, they take before suffocating. So these are not things that we want to see. So there is a strong need to protect. And to this, and in order to do this, and for economical reasons, 5 different scenarios or protection profiles have been defined. Scenario 0, no specific security. There's no telecommand authentication and encryption, and no encryption on the downlink of the data. The links, the terrestrial link security is standard, is what you would normally do in a normal installation. Firewalls, secure VLANs, vetted personnel. This has actually worked for many, many years in the past Earth observation missions, ERS and ENVISAT and Earth Explorers. These missions I haven't introduced because they are past. They belong to history. They are very glorious, and they are now, the spacecraft are decommissioned. They were not deorbited because this is before the code of conduct, but they are not operational anymore. Of course, the amount of data is all available, and this is unprotected, so everybody can get the historical data of the space missions. The scenario 1 is, let's say, the minimalistic scenario, static telecommand protection. The telecommands are authenticated and sequenced, so there is a counter. But the authentication keys are all preloaded on board. So they were put on the spacecraft when the spacecraft was launched. And the authentication keys have a lifetime, which is prorated respect to the lifetime of the spacecraft. Now, an important point, which is critical to cryptographers, for example, for me, it was very critical. You will see it in all scenarios. The telecommand authentication can be enabled or disabled automatically by ground. This is a requirement by all mission managers. They accept the requirements of security, but they say yes, but there must be a situation, which is the typical critical situation of the spacecraft, where all possible ways must be undertaken in order to save it, where the telecommands can be disabled so that the crypto doesn't become a blocking element for the saving of the spacecraft. This can happen and has happened. So thanks to this, many of the spacecraft have been saved in particular conditions. And this is currently implemented on METOP. Going more security, dynamic telecommand protection provides authentication and anti-replay of the telecommands, but the authentication keys can be rekeyed using master keys. So at the moment of launch, we create only the master keys, and then we have a possibility to create session keys at different times according to the amount of data being sent, rekeying the keys that are used for the transmission of the data. The scenario 3 is the same as before, but with a payload data protection so that we can protect the data. This is typical for scenarios where the data is sensitive in its nature, so that the data policy provides for protection of the data. The last one, that scenario 4, is the most secure, is the one where also the housekeeping telemetry data is encrypted. And this is typically leading to Galileo, because the housekeeping telemetry is the data that provides the signaling of Galileo. And to conclude, the Galileo system security is the one that implements the scenario 4. For the protection of Galileo, extreme measures were taken, like all ground stations have been located on territory of European member states, of ESA member states, including in particular Norway, which is very interesting because they have a lot of land in the Arctic, and that's where the ground stations must be, because most of the satellites in polar orbit pass over the Arctic. So very important, politically, no ground station of Galileo is anywhere but in European land. And we have to thank France that have kept the empire, because France has territory everywhere. And so there's always a French island somewhere. Much less the UK. Switzerland is no use because it's all here. And then in South America, it's tricky. So some treaties have to be made in Argentina, thanks to the links with Spain. So the politics of these things is extremely complicated. For the other example is GMES, also called Copernicus, the Earth observation, the Sentinels. For them, scenario 2 has been chosen. So dynamic telecommand protection and using the keys to create other keys, so master keys. Okay, I will go directly to the conclusion. The general increase in the attractiveness of space assets is making the cyber threats to the missions more and more realistic. From the past, when there was simply some glory and some nice fame to be made for having hacked the satellite, now we are coming to the fact that some of the data have critical and strategic nature, and so they become attractive to many, many powers. The fact that the basic technology is available more commercially is making also possible for people with bad intentions to access. The protection of critical infrastructure is critical, and that's why politically we need to have the recognition as critical infrastructures. Then more at the point of IT security, so this is a message mostly to those who are fighting in the cybercrime arena in Europe. The key is collaboration, so we have established relations between the CERTs, we share experiences, and we define common protection rules. And this goes in the direction of something said before. Since the internet is not secure or doesn't have basic security capabilities, what is necessary is to create inside the internet user communities that share, for example, a set of keys, share a set of virtual links, VPNs that can be created on top of the internet in order to make secure the communication between well-defined parties. And this is the end. Thank you very much. Any questions?